Okay, I have chat open here. Okay, so today we will be by the title of the class, can't attend today's class. Okay. You can watch the recording. Bye. Okay. So today we will be proving the fundamental theorem of algebra. Uh okay, so everyone knows what the fundamental theorem of algebra is, I think, but I'll just recap. So is my voice really that bad? I can fix it. Let's see.
Is it better now?
Very much. Yeah.
Yeah,
It's
fine.
100% better.
Okay, fine. I'll use this then. No more headphones. Well, hello. Hi. So, this is like advanced math. I don't think that we'll do much problems. Well, let's see. I If anyone wants buffer problem, try to complete the whole proof on your own. I- eh, Okay. Anyway, so fundamental theorem of algebra. Everyone knows this, I think, but like the statement, it states that every polynomial, mm, wait, every polynomial in with complex coefficients. So for those of you, this means like the set of all polynomials with complex coefficients, such that p is not a constant. Has a complex root. You might have seen this as like has as many complex roots as its degree, but that's fine because like if it has one root, you factor it out and you get a polynomial of a smaller degree, which also has a root, and then you factor it out, and then you keep going until you get n roots. So a polynomial has as many roots as its degree. So, and we want to prove this theorem. Yeah. Okay. So first of all, I'll start with like a small lemma. Um, suff it suffices to show this theorem for polynomials with real coefficients. So the theorem states that every polynomial with complex coefficients has a complex roots. If you can show that every polynomial with real coefficients has a complex root, then you're already done. That is my claim. Okay, can someone just prove the lemma?
Try to separate the imaginary and real parts if the coefficients are complex.
Okay. So like take px, write it as gx plus I times hx.
What's the statement again?
So suppose you have proven that every polynomial that has real coefficients has a complex roots. From this, can you prove that every polynomial that has complex coefficients has a complex root?
Can you look at P conjugate or something?
Yeah. Yep. So P conjugate will be g of x minus IH of x. And you know what? I'll start writing of x from here on because I'm tired. And after P conjugate, what do we do?
Can multiply because you want some real coefficient popping up. So
Correct. So P conjugate, that's g square plus h square. Uh, this has real coefficients. So we know this has a real root. This has a complex root, say z. So like P of z times P conjugate of z is 0. So either P of z is 0 or P conjugate of z is 0. But, well, if P of z is 0, then P of x has a root. What if P conjugate of z is 0?
Z conjugate. Oh yeah, right.
Z
That's
conjugate
my
as a root. Yeah, perfect. So if we prove the theorem for real polynomials, we prove it for all polynomials, called complex polynomials. Is that clear?
Yes.
How does Z con like how does P conjugate Z proves that? Like Z conjugate कैसे root है?
Okay, so like there's this like P of Z conjugate equal P conjugate of Z. Well, it is like this. If P has the real coefficients. No, wait.
Yeah,
Oh.
so like the P
Sorry.
of Z conjugate is equal.
No, wait. Yeah, okay, no. Sorry. Yeah, so P conjugate of Z is 0, right? So like AI Z to the n, like summation AI Z to the I is 0. So take conjugate on both sides. Summation AI conjugate Z conjugate to the I is 0. Right.
Why is this something? I mean, it's kind of.
Like I expanded P.
And don't use I, right?
What?
Don't use I.
Oh. Yeah. But probably not a good idea to use I for indexing in this class. It's J. Good. Now, electrical engineers will come and tell me J is also the imaginary unit, but no one cares about them. Yes. Yeah. So the point is, if the conjugate, like if the coefficients of P conjugate are AJ, then the coefficients of P are AJ conjugates. And like summation AJ conjugate Z conjugate to the J being 0 is like equivalent, same as like P of Z conjugate being 0. Right. Is that clear?
Yeah.
Yeah.
Yeah. Okay. So that's lemma 1. Lemma 2 is even okay, lemma 2, I will not prove, I'll just state. Every real polynomial of an odd degree has a complex root. Can someone just, I mean, okay, we'll give an informal. Can someone just tell me how to prove this?
Intermediate
You
value.
mean real root?
Yeah.
You mean real root?
But complex numbers are real numbers. Sorry, real numbers are complex numbers, so it still works.
Yeah,
I
okay.
really-
Complexes come in conjugate. So that's
What?
complex roots comes in conjugate. So
Yeah. So
Yeah.
it's fine. Oh yeah, even no. What you said doesn't work because we have not yet proven that this definitely has roots, right?
oh,
Yeah, but like intermediate value theorem works. The degree is odd. So if the leading coefficient is positive, say it's like 5x to the 3 plus something, then at infinity, this will be like infinity. At negative infinity, it will be like negative infinity. Or like to be more formal, at like large capital N, it will be a large positive number. At large negative N, it will be a large negative number. Somewhere between them by intermediate value theorem, it's 0. I believe Rushil took an analysis class at some point. I don't know if he covered intermediate value theorem proof in that.
It wasn't here.
It wasn't here.
Yeah.
It
It
doesn't
was
matter.
easy.
Uh, intermediate value theorem is like not that hard to prove, and I hope you guys are like fine accepting this for this proof. You can otherwise you can like look up the proof. It's not that hard. And I think I don't think anyone will have issues with this, I hope. So that's now I'll mention lemma 3. If a plus b is a complex number and ab is a complex number, then a and b are complex numbers.
Isn't this obvious? Like A and B
Yes,
would
it is.
obviously be
It's
complex.
completely obvious because you solve the quadratic equation and you know the quadratic formula and you know how to take square roots of complex numbers. This is perfectly obvious. But
No,
these three
like
lemmas.
you have like when you define this sum, aren't you itself taking A and B to be complex? Like A plus B can be
Okay. Yes. Okay, so this lemma actually is like I'm scamming a bit. Okay. You have a point. But okay, it will be more clear later on. But okay, assume that like something A and B are part of something like larger than the complex numbers. But the thing is, you can still solve for A and B, so they are in fact complex numbers.
Like
Yes, aren't all numbers complex? Okay, you guys raised good points, and okay, you can ignore lemma 3 for now. I will explain it further when we get into the deeper stuff. But like lemma 1 and 2, I think everyone's clear. And okay, lemma 4, it is a theorem. It is in fact another fundamental theorem which we will use. The fundamental theorem of symmetric polynomials. Symmetric polynomials. Okay. So suppose you have variables x1 to say xn. Then a symmetric polynomial in x1 to xn is a and b quaternion. Okay, quaternions don't count because they're not a field. I'll get to it. Wait for me. Yes, so x1 to xn. A symmetric polynomial is, well, any polynomial which is like completely symmetric in x1 to xn. So like summation xi square is symmetric, but summation like xi plus 1 is not symmetric. Right? Everyone, like any permutation of x1 to xn gives the same polynomial. That's what it means to be symmetric. Everyone knows that. I mean, that should be clear to everyone. So the elementary symmetric polynomials, which are either denoted by the letter S or the letter rho, and I don't remember which. Does anyone remember?
Just denoted by anything. It's
Row. It is row.
It's rho?
Yes,
It's rho?
Yeah, it's
Okay. So
isn't
rho
it
1,
sigma, not rho?
oh, there's a reason I didn't do physics. So, okay, rho 1 is summation xi. Rho 2 is defined as summation xi xj for I n equal j. And rho 3 is defined as summation xi xj xk for ijk all distinct, and so on. Basically, the point is, if you consider the polynomial x minus xi, the product, you will get x to the n minus rho 1 x to the n minus 1 plus rho 2 x to the n minus 2, and so on. These are the elementary symmetric polynomials which appear as the coefficients, right?
Symmetric polynomials are not polynomials, right? They're just a form of.
They're polynomials in multiple variables.
Okay, yeah.
Yeah, that's what I call it. Yes, so like we have symmetric polynomials, which are all of them. Yeah, Newton's identity, basically. We are getting to it. And the elementary symmetric polynomials, which are the specific symmetric polynomials that appear as the coefficients. And I think rho 0 is defined as like 1 or n, but I cannot care less. No, I don't think rho 0 is even defined. I think S0 is defined. It does not matter. We only care about these. Yes. So, okay. Suppose someone tells you the value of all the symmetric polynomials, rho 1 to rho n, and then ask you to find summation xi square. What do you do?
I mean, rho 1 whole square minus rho 2.
Minus 2 rho 2. But yeah. So yeah, given these, you can find summation xi square. Xi cubed. Anyone remember?
Yes, we can actually use like 3 times rho 3
Okay, 3 times rho 3
plus rho 1
plus rho
1
1.
whole bracket. No, like bracket only on rho 1.
Oh, okay, why do you need a
Yeah.
bracket for that? Okay.
Yeah, so we can now it's rho 2 minus no wait, it's rho 1 whole square minus 3 rho 2.
Rho 1 whole square minus 3 rho 2.
Yes.
I'd believe you. Wait, why are you writing it like this, guys? Minus 3 rho 1 rho 2 plus 3 rho 3. Does this make sense? So this is summation xi cube. So that will be like summation xi cube plus verify this. And if it's wrong, blame him. I believe you. Anyway, so the point is what I'm trying to build up. If you're given the symmetric polynomial, elementary symmetric polynomials, you can find any other symmetric polynomials in terms of them. So like I was going with like xi to the n, and in fact the formulas for all of them are like well known as the Newton identities, which are relatively useful. But we want to prove it for like all symmetric polynomials, like say summation xi square xj squared. any random symmetric polynomial, we want to say it can be expressed as in terms of elementary symmetric polynomials. More formally, it can be expressed as a polynomial function of the elementary symmetric polynomials. We are all calling it a row. Oh yeah, this is row now. I don't care. So the statement of the theorem is clear. So this is what we'll try to prove now. So given any general polynomial, how will you try to express this in terms of it? Yeah, they do. Newton identity have very cool proof. Unfortunately, like I don't want the identities, I just want to show existence. I don't care about what the specific formulas are. So, isn't it a row only? Yes, yes. Everyone who's telling you otherwise is spreading fake news. This is row. So how can we try to prove this? Showing existence, bringing back to memory when we played axiom of choice to every. Yeah. Okay. Any ideas for this? So okay, let this be the first. We want to prove the fundamental theorem of algebra, but the first problem of this class is to prove the fundamental theorem of symmetric polynomials.
Can you scroll up a bit and show which polynomial was involved in this? Like, yeah, in this, let's say x1 cube, we find x1 cube. Which polynomial? Can you write the polynomial? Like, what is the polynomial used? Like x1 cube minus 3, sorry, row 1 cube minus 3, row 1, row 2.
Row 1, row
What is
2
the
plus
polynomial
3.
involved there?
What is?
Polynomial involved there, like.
No, this is the polynomial. So like, consider a polynomial, like polynomial and multiple variables.
Oh, okay.
Yeah, sorry. I should have made that clear. Like f is a polynomial in n variables.
Okay.
So like the polynomial involved here is x cubed minus 3xy plus 3z. And you plug in x equal row 1, y equal row 2, z equal row 3.
Okay.
I joined late. Can I say? Yes, okay. So while everyone thinks of this, I'll just quickly recap what we have done. So I stated the fundamental theorem of algebra. And okay, so the first lemma was reducing that it suffices to prove the fundamental theorem of algebra for only polynomials with real coefficients. So like if you have a complex polynomial, you multiply it by its conjugate and you get a real polynomial. And if all real polynomials have a root, then like then all complex polynomials have a root because you can always multiply complex polynomials to get real polynomials. Right. So this is lemma 1, that we only have to show fundamental theorem of algebra for polynomials with real coefficients. Lemma 2 is if degree is odd, then there's a root, which is intermediate value theorem. Lemma 3 is coping. We'll get back to it because people saw that I was trying to scam them. And
Wait,
okay, lemma 4.
why was lemma 3 copying again?
Because, okay, what are A and B? I'm saying A plus B is a complex number and AB is a complex number. But what do I mean? Like, what are A and B? I have to like start by saying something, right?
Oh, okay.
Or A and B and something. And if I say something is complex number, then like the last statement is vacuous. Lemma 3 is true because yeah, it's vacuously true, but like no, it's deeper than that. Anyway, so fundamental theorem of symmetric polynomial. Yeah, now we are doing the fundamental theorem of symmetric polynomials. Yeah, okay. So a symmetric polynomial is any polynomial which is symmetric in all the variables. And so like given x1 to xn, the elementary symmetric polynomials are all these like Vieta coefficients. So sum of x1, sum of x1, x2, sum of x1, x2, x3, with xi, xj, xk, right? And the fundamental theorem of symmetric polynomial states that given any any symmetric polynomial, you can express that as a polynomial function of the elementary symmetric polynomials. So like summation xi square, you can express it as ρ1 square minus 2 ρ2. And like this is a polynomial, like when I say polynomial, I mean polynomial in multiple variables. So ρ1 and ρ2 are the variables. So I say like no matter what symmetric polynomial you put here, you can find it as a function of the elementary symmetric. Is the statement of fundamental theorem of symmetry clear, Kushagra?
So like you are trying to basically say that we define these symmetric polynomial functions, and then any other symmetric function can be expressed in any form like via these symmetric polynomials, right?
Yes, basically. But the thing is, all the forms are polynomial, never introduce square roots or signs or whatever. But yeah, that's
Okay,
basically it.
sure. Thank you.
Okay, so I'll give you a
Can we
this
induct
is
on this somehow?
induct on what?
Like the
You
degree
can.
of the new symmetric polynomial.
Yes, good idea. Good idea. So you can induct on the degree, but okay, but you can do
X1,
better.
X2, X3. We could have like any degree, and then it could be of any form like X1 square, X2 cube, and X5, something like that.
Yeah. Yeah. So like, wait, how are you defining the degree of a symmetric polynomial?
The sum of the degrees of
Yeah. Okay.
the powers.
That is how you define like degree normally. Inducting on that is a little bit hard. Can you define like some other notion of degree that like, okay, the point is when you have normal polynomials, say you have a like single variable polynomials, you have x to the n plus ax to the n minus 1, whatever. So if you want to like go from n minus 1 degree to n degree, you only have to get rid of like one term, x to the n. But when you have polynomials in like multiple variables, then say two variables, then the thing is, like if it's degree 5, the thing is there might be like multiple different degree 5 terms, right?
Ah, okay, I get it.
Can you make some way to deal with this?
I
So
mean,
like,
just consider y. Just consider y at its degree.
Consider only y.
Yeah.
can you just like choose to like look at all the degree 5 terms and say all polynomials with only degree 5 terms can be done,
Okay, sure. Okay, yeah. First of all,
and
that's
then
great.
add
So
those back?
take any polynomial and you're saying like split it into its homogeneous parts. So like
Yeah.
sum of all degree 5 terms plus sum of all degree 4 terms plus sum of all degree 3 terms, and just try to express each of them individually.
Yeah, the largest one, because you can.
Yeah, okay, express the largest one and like, yeah, fine. So you only have to prove the theorem for homogeneous ones. That's fine. Okay, so you have reduced to homogeneous. Now all the terms have like the same degree. And now what do you do?
Now just take one variable and consider that. I think.
What?
Just take one variable like y5,
Okay.
y4.
Okay, so suppose if you only have two variables, then like okay, sure. Let's start with two variables, suppose. So suppose you have a polynomial in two variables that's homogeneous.
It
What do you do?
induct on the number of variables. Is that-
What?
Can you induct on the number of variables of the symmetric polynomial? Will that be-
Possibly, but I don't know. That's not the proof I'm aware of. Maybe it's possible. It might be possible. Wait. Yeah, wait. Okay, can someone one by one who was talking before about just take
Yeah, just take one variable
yeah.
and consider its degree.
So okay, so suppose I take x2, and then we have so okay. Suppose I'm now ordering the terms by their degree in x2,
Yeah.
right? So now what do I do with this? Like it starts with how will you induct?
So I mean, like you're asking to just define degree in a different way. So
Yes, but how will you use this?
mm,
You are correct, but
okay, like
thing. It's fine. Let f be the symmetric polynomial with quotients in I am field. You're a field. Yeah, but in field K. Yeah. Yeah, I figure. Okay, just prove the theorem for the idea is correct. You need to induct on degree. So like for two variables, first you reduce to the homogeneous case, which is fine. Then you in homogeneous case, you have a new notion of degree now. So like since you're only looking at homogeneous polynomial, you define the degree of it to be like the degree of the highest coefficient of x2 that appears. So like suppose we want to prove for all homogeneous polynomials of degree 5, like this is the original degree. So like p equal x cube y square plus x square y cube. So you call this degree 3 and p equal like y to the 5 plus x to the 5. You call this degree 5. So now you want to induct once again. Like how will you go from degree, well, degree 1 doesn't actually exist anymore, but because they won't be symmetric, but how will you go from like degree 3 to degree 4?
You just multiply by x plus y, like something like that, or sigma 1.
Yeah, okay, but that changes like this. Then the total degree changes. Like you want to induct on like the same original degree, right? And I would tell you like it's better to try to induct downwards. Like take this and like show that like try to convert this polynomial into a polynomial of a lower degree by subtracting homogeneous polynomials from it. Yeah, it's too much. So like start by x to the 5 plus y to the 5. And we are defining degree in terms of y. You just want to get rid of the highest degree term, which is y to the 5. How will you do that?
Minus of
Just subtract
rho
y to the
minus sigma 1 to the 5.
Correct.
Rho
Minus
1 to the 5.
Yay. Correct. Minus rho 1 to the 5. Yes, this gets rid of the y to the 5 term, so you'll get a degree 4 polynomial. Now suppose you have a random degree 4 polynomial. So that would be y to the 4x plus smaller degree terms. How will you get rid of like a times y to the 4x?
a times sigma 2 or something.
A
Sigma
times
1.
sigma 1.
Sigma 2. Like sigma 1 square, sigma 2 something.
Yes, perfect. And so you do need to verify one thing. Why does this like, yeah, okay, this works. Because the only y to the 4 term you'll get is y to the 4x. And you get rid of it. So you get a polynomial of a smaller degree.
Can you repeat this power 4 part?
Which part?
This power 4.
Yeah, so suppose you have like a polynomial where the highest degree of y that appears is y to the 4.
Okay,
Right.
yeah.
Say it appears like a y to the 4x plus terms which have a smaller y degree.
Okay.
So you subtract a times sigma 1 square, sigma 2. So sigma 1 square, highest y term is y square. Sigma 2 is just xy. Oh, this should be
Sigma
cubed.
1 cube, I think. Yeah.
This should be cubed. I'm sorry. Y cube and xy.
Yeah,
So the
my
highest
Now
is
it
xy
works.
to the 4. Yeah, it's clear?
Yeah.
Yeah. Okay. So you can sort of see how you can do this, but let's try to do this. What about 3 variables? Can you
again,
Now
like
get
know stuff about 2
now you
variables.
do
Use that.
sigma 1, sigma 2, sigma 3.
yeah, okay. What notion of degree are you using?
Again, like okay, now this time how will you do it?
Yeah.
Take like sigma 3 to the power something such that one of the variables like becomes 0 in power, like something like that. And then we keep on reducing it, so to say.
Yeah,
What?
but
Can
how
you?
are you defining degree for
Yeah.
3 terms?
Yeah, like no, we just look at x1 to the power m, x2 to the power n, x3 to the power l or something. And then we take sigma 3 to the power l, let's say if l was minimum. And then we take sigma 3 to the power l. And then like that means that x3 term is like done, and then we can just do x2 and x1.
I'm not sure what you mean. Wait, the issue is like if you're only looking at like degree of one thing, the thing is so x3 x3 to the 5. Now it can come with like x1 square x2 plus x1 x. There can be multiple terms corresponding to it, right?
Correct. Yeah. No, I was talking about like you take one of those terms and we resolve that, right?
Yeah, but which order do you resolve them in?
Like in the smallest to like the largest, because like the smallest, then we can remove all three in one go. Like this is
How are
like
you
very
defining smallest? Like that's what I need to know.
Smallest
smallest
index.
of the three
Index.
powered.
Powers, what? This is 2, 1, this is 1, 2.
Yeah. So
Uh,
okay.
I mean, just take the smallest index or something.
Yes, yes, yes. That's basically the idea. So like, wait, I'll just tell you this because we have a lot more to get to also. And yeah. So the idea is that, so what did we do? When we had, so we define degree like this. First start with x3. Like whatever is the highest degree, you take that, x3 to the 5. Then like look at all terms corresponding to x3 to the 5. Whichever has the highest power of x2, you take that. Then look at all terms with those. Whichever has the highest power of x1, you take that. That's how you tie break. Just look at the
Yeah.
small
So
next
like,
thing.
yeah, essentially doing it with the index ordering.
Yeah, that's what you were saying. So the way is like also in general for any polynomial, the way you order its terms is first you order by like sum of degrees, then by degree of xn, then by degree of xn minus 1, and finally by degree of x1. You use this as an order. Now I get it. And you said, okay, fine. It will get, sure, yes. Anyway, so now you take the highest degree term, and what do you do? So suppose the highest degree term is xn to the k, xn to the, let's call it an, xn minus 1 to the an minus 1, and so on. For an greater than equal to an minus 1. Yes, okay. Why must this be true? Why must an be greater than equal to an minus 1?
We defined it like that.
No. So thing is we have ordered by, so suppose we have,
Yeah, again, like we have ordered, right, in terms of indexes. So we have taken the highest
right.
power of xn, then the highest power of xn minus 2.
I'm trying to think how I get this. Wait, how I say what I'm trying to prove. x3, x2, x1, x3, no. So 3, 4, and say 0. And we have like 2, 1, and like wait, total is 7, right? 4. So suppose if these two are terms, 2, 1, 4, and 3, 4, 7. So like this term will win, but 4 is bigger than 3. Because the way we do is we first look at the sum of degrees, both is 7. Then we look at just the power of x3, and this wins. Is that clear? Like, why this
Yeah,
is winning here?
I think it's somehow like a majorization argument.
Yeah, but the
But
point
like,
is P is symmetric.
So there must be a 4
Yeah,
x3 to the power 4 and x2 to the power
Yes,
3.
exactly.
Like we
So
can
like
just
if
swap
3,
it.
4 exists, then 4, 3 exists, which is larger.
yeah.
Yeah. So like all the questions are ordered in like decreasing order.
So like
Right.
it's like they become three groups, each of which xi is power 4 something.
Yes, yeah. Like the point is for any term that exists, there exists a term where its powers are arranged in descending order, and that term is like of the highest degree in like this new notion of degree we have defined.
But then eventually we'll have to deal with this unordered part, right?
Which another part? Oh no, but that's the point, right? The thing is it's symmetric. So if we have gotten rid of the ordered part, then we have to get rid of everything else by symmetry because we are only working with symmetric polynomials.
Okay, yeah, that makes sense.
So,
Like the
So okay, I'll just
the notion changes, but the proof remains same.
exactly yes. So so suppose we have like xn to the 7. I'll just give you an example and you can like fill in the details yourself. Xn minus 2 cubed and say like and say this is 1. So suppose this was 2, this was 3, this was 4, 2, 1. So now what you do to get rid of this term, you subtract. So first you subtract row 4.
Row
So
4
row
is
4
the...
means like 1 in each, right?
Yes. Now, yeah, that's what I was trying to say that, like that.
Yes. So now you do row 2 squared. So like the highest term you will get will have a power of 2 in each, right? X4, x3, x2. So now you have gotten rid of x1, you have gotten rid of x2 cubed, and you're left with like x3 cube and x4 to the 4, right?
So again, sigma 1
Yeah, wait,
cube.
row 4, this is row 3. And this is row
Sigma 2 cube, yes.
row 2 cube and row
And
1.
sigma 1 4.
Yeah. Right?
Wait, sigma 1 4.
No,
Is
no,
it?
no, because when you get rid of 6 powers of this, you also have already gotten rid of 6 powers of this. And only one
Yeah,
power is
one more. Okay, that's it.
sigma 1. Yeah. And like the thing you need to verify is that this doesn't introduce any terms which have a higher degree. But like the thing is, the reason the notion we have defined is good is because if you add terms of large degrees, they get terms of large degrees. Like this is a nice order. So like the point is the highest degree term in row 4 times the highest degree term in row 3 square times the highest degree term in row 2 cube times the highest degree term in row 1 is this term, right? So any other term that you get must be of a lower degree than this term.
Yes.
Is that clear? You have to verify that the like notion of addition still works in this new notion of degree. Like if degree of A is less than degree of B and degree of C is less than equal to degree of D, then degree of like A times C is less than equal to degree of B times D. But this is a very easy verification. Anyway, is with so much intuition, proof should be left as exercise. Actually, fair. Yeah, I think everyone can complete the. I mean, I have already basically completed the proof. Everyone understands the fundamental theorem of algebra, no, fundamental theorem of symmetric polynomials.
So aren't we just inducting? Like, aren't we just inducting on the number of terms only?
Yes, but if you want to call it, we are being a little bit more careful than that. Anyway, we have done enough warm up. Now let's get to the proof. So, if anyone doesn't even have any doubt in lemma 1, lemma 2, or this theorem, left as an exercise. Okay. This is now you're just trying to bait me. Yes. Now we will, without further ado, we will prove the fundamental theorem of algebra. I'll get to it. I'll explain lemma 3. Okay. So, we only want to prove every polynomial in reals has a root in C. So, for polynomials of an odd degree, we are done. Intermediate value theorem. We will now use induction. We will induct, so if P has degree n, we will induct on V2 of n. So we have proven it for odd. Now we'll prove it for 2 times odd. Then we'll prove it for 4 times odd, and so on. We'll induct on the power of 2. 2 to the 1.
Are we inducting up or inducting down? Just to say.
We are inducting up on the power of 2.
Okay.
Right? Okay. So for odd, we have proved. So we'll try to prove it for 2 times odd. So let's start with 6.
Is the odd proof just lemma 2?
What?
The odd proof is just lemma 2?
Yeah, odd proof is lemma 2.
Okay.
Okay, 6. So suppose we have a 6-degree polynomial that does not have a complex, for the sake of contradiction. For the sake of contradiction, we have p of x, which is degree 6, and it does not have a complex root. And divided by constant term, it's monic. What did we just do for the proof of algebra theorem, please? Wait, what? We are inducting. We have proven it for all odd numbers. Now we'll prove it for
But
all
odd,
odd numbers.
for odd, we just gave one root, no?
Okay, yeah, okay. I think you, like, as I mentioned at the beginning of the class, the fundamental theorem, I'm just proving every polynomial has one root. After we have proven everything as one root, we are done. Because take a polynomial of degree n, factor that root out by factor theorem, you have a polynomial of degree n minus 1. Apply the theorem on that polynomial again, and take its root out.
But wait, if we do that, then the odd degree will become like something like
Even degree,
one
yes.
linear times in even.
Yes,
Yeah.
yes.
So how
No, but
can
the
we
thing is,
assume that?
so no. First, I'll prove odd degree has one root, then 2 times odd has one root, then 2 square times odd has one root, and so on. After I have proven everything has at least one root, then I'll get to that everything has n roots.
Okay.
First, I'm just proving everything has one root, at least one.
Okay. Yeah.
Okay? So, take a random polynomial of degree 6. Suppose it does not have a complex root. Okay? So, when was the last time we found a polynomial that didn't have a root? It was x squared plus 1. We were looking at this polynomial x squared plus 1. We realized it does not have a root. So we decided that the real numbers are not good enough. And we went to a new system of numbers, the complex numbers, which were good enough. And in that it had roots. Let's do it again. So now this polynomial, it does not have a root in complex numbers. Hence, they are not good enough. So we'll go to C star, in which it does have roots.
Oh,
In
then
fact,
you can get the
Okay, no.
symmetric polynomials, right? By
Okay,
the
no, like,
coefficients.
how do we prove that such a number system
Yes.
exists?
Exactly. This is proving such a number system exists is non-obvious, and I will prove it. But first, for now, assume such a number system exists. I'll complete the proof, and then at the end, I will show this number system exists. Because I think like the intuition of this proof comes after this. Existence of the number system is a separate part, which I will cover. Do not worry about that. Okay.
We have all the symmetric polynomials of its roots, correct? Like,
Yes,
like we can write it in this new number system. So
yes, at least define the number system, bro. Okay, I will. This is okay. So for now, except there exists a field, which means like number system, as in you can multiply, subtract, add, and divide here. Well, you can't divide by 0, but you can do everything else. And this system is such that P of x has roots. In fact, P of x, let's say, has all 6 roots. I go like so high that like P of x completely factors. Like complex numbers were not good enough. I need this polynomial to have roots. So I'd say it has 6 roots. I need you to accept that this number system exists for now. I will prove it exists. I will prove there is a number system which has 6 roots. For now, we assume it has. I mean, complex numbers are a number system where it has 6 roots, but we don't know that yet. How are you defining this number system? Okay. What do you mean?
Wait, are you adding
I
components
think
or something?
you can just define the number system as something whose subset is complex. That's what you wrote.
Yeah, exactly. That's what I'm saying. I will. Yeah, okay, Gupta,
Okay, like
I'll
so
get
for now we just assume that the like solution exists over a new kind of number system, right?
new kind of number systems which are larger than the complex. You add like you had I, you add j, k, l, m, which satisfy random relations. I don't care. It exists. It happened. Anyway, so now in this number system, we use factor theorem. So this polynomial factors as x minus z1, x minus z2. I'm no, that's fine. When I first saw this, I had like a lot of questions. I will get with assume for now. Okay? You don't need to defend me. Okay. In this number system, this polynomial factors. That's how I defined it. Like that's the number system I took. I specifically took a number system such that this polynomial can factor perfectly. Z1, Z2, Z3, Z4, Z5, Z6. Now, what I want is some of these to be complex numbers, but I don't know that yet. So here, what I do is I write a new polynomial. Let's call this P naught of x. Okay. So this polynomial is x minus z1 minus z2 times x minus z1 minus z3. And it's basically dot dot dot. I product of x minus zi minus zj I n equal j. Okay. I write down this polynomial.
Wait, what's the motivation behind writing
Why
that?
are we doing this? Like, what?
I'll explain. Wait, give me a second. Just give me a second. Yeah, okay. I write this product down because tell me what its degree is. Look, I know the motivation seems lacking, but
Six.
what? No.
Wait,
This
wait,
new polynomial.
okay. So
X
it
choose
ranges
two.
How
from
do you
6 to
even
8.
know this has real coefficients?
X choose.
Okay. We'll get to that.
And
6 choose.
choose 2.
N choose 2.
6 choose.
Oh,
N
it
is
ranges
6.
from
6
2
choose
and
2.
15.
15, which is an odd number. Would you look at that? In fact, if n is even, n choose 2 has one less power of 2 than n.
So it has complex roots.
No.
And
Okay. You need to verify one thing. Like, the coefficients of this polynomial, are they even real numbers?
Oh, symmetric polynomials, that whatever.
Symmetric polynomials. All the coefficients are symmetric polynomials in z, like all the zi's. Hence, they can be expressed as polynomial functions of the elementary symmetric polynomials. And the elementary symmetric polynomials are
Lemma
just the coefficients
3.
of px.
wait,
So they are
repeat
real
the
numbers.
statement.
So the coefficients of this are real numbers.
Can you repeat the statement?
No, it's not done. It's not done. So now all we know is odd polynomials have one complex root. We don't know all of them are complex. All we know is that some zi plus zj is complex. There.
Similarly, we'll
Lemma
define
3.
mother P
So
naught
now
delta to
explain
the
as
x
z i
minus
zj.
zi zj, x minus zi times
I'm
zj,
coming.
and we apply lemma 3.
But first we have to wait, like lemma 3, like I didn't get it.
I'm getting to it. I'll get to everything. So does everyone see like some zi plus zj is a complex number?
Also, can you repeat why that real coefficients are? I couldn't
Yeah.
get that.
So all coefficients of this will be symmetric in all the zi's, right? If you expand this out, like you will get the same power of z1, same power of z2. There's no difference,
Yes.
right?
Yes.
So it's a symmetric polynomial in zi and z, like z1, z2, z3, z4, z5, z6, right?
Yeah.
A symmetric polynomial in them can be expressed in terms of row 1, row 2, row 3, and row 6. Right?
Okay.
Yeah.
And row 1, row 2, row 3, row 4, row 5, row 6 are the coefficients of P of x. So they're real numbers.
Oh, yes. Okay. Yeah.
Yes. Okay. Now I will write P1 of x. So nice. P1 of x will be product x minus zi minus zj minus zj. This is again a degree 15 polynomial. Due to symmetric stuff, this has at least one complex root. So there exists I and j such that zi plus zj plus zj is a complex number.
I think you should use K and L because like the
Yeah,
ING
because
is not the same.
they can be different. That is the issue. If they were the same, we would be very happy, but they can be different. Yes?
Yeah.
Okay. Now, in general, I will define Pn of x to be product. This is black magic, by the way. This actually is. This proof is completely black magic, but it is incredible. Minus n times zij. So we will get, there exists, I'll call them in comma jn. I'll index the I and j further, such that zin plus zjn plus n zin. People are arguing what is the most black magic. Good. This is a complex number. This is true for all n.
So just choose like lose PHP and find two which are like the same thing.
Yes.
There's no
Yes.
motivation behind this.
It's incredible.
Can you repeat what you even did? I didn't get this.
Yes.
Okay. So do you understand like when I defined P1?
I understood the definition, yes.
You understand the definition of did you understand P0? Wait. Do you understand the definition of P0?
Yeah, yeah.
So you understand it has real coefficients.
Yes.
So it must have at
That-
least one complex root.
That's the part I didn't understand. How does
Yeah.
it have real?
Okay, wait. I'll come back to that. So it has real coefficients. So it has at least one complex root. And its root we know are zi plus zj, right?
Yeah.
So some zi plus zj is a complex number.
Right.
Now define P1x similarly, but like instead of zi plus zj, you have zi plus zj plus zi zj. Right.
Yeah.
So once again, you'll have like some number of this form is a complex number.
Okay.
Exact same, right? Understand?
Oh, okay. Yeah.
And similarly, you can conclude like some number of like for every n, there is some number of this form that is a complex number. Right?
Yeah. Okay.
Now, there are Z1 to Z6. We have like 6 numbers. So there are 15 different pairs you can have of Zi and Zj. Right?
Yeah.
Go from n equals 0 to n equal 15. These are 16 different numbers.
Yes,
These are 16 different numbers. So
that-
two of them
Yeah.
must have the same corresponding pair. Like all of them can't give different pairs of Z I Z J because there are not enough pairs. Pigeonhole principle. Is that clear? So like for n equals 0, we get some pair I0, I0, J0. For n equal 1, we get some pair I1, J1. Eventually, we will have two pairs that are same because there are finitely many pairs. Pigeonhole principle.
Okay.
Is that clear?
What if
Yeah.
2C2 is even, not odd?
What? 2C2?
Oh, acha. 2C2 will be even only when it is power of 4. So, okay.
Yes.
It is
The lemma we are using is this, like V2 of NC2 is less than V2 of N when N is even, for N even.
yeah, okay, yes. So,
yes. Anyway. So we have two numbers. We'll have two things that have the same. So we get, suppose they are Z1 and Z2. So we get Z1 plus Z2 plus say 3Z1 Z2 is in C. Z1 plus Z2 plus 7Z1 Z2 is in C. Now these are two linear equations. Say this is a complex number, say x, this is a complex number, say y. You solve these two equations and you will get like equations in Z1 plus Z2 and Z1 Z2. These are linear equations. So you can get like Z1 plus Z2 in terms of x and y. Say you get W, and Z1 Z2 you get as, okay, the next letter is Z, which I don't want to use. What's P and Q. Z1 plus Z2 is P, Z1 Z2 is Q. Lemma 3. Now, if you don't want to use lemma 3, what I will tell you is this. P square, no, sorry. What do you want? P by 2 plus, just write this quantity. This is a quadratic formula. You write this quantity, you will get that this is Z1 or Z2, depending on whether you choose which branch of the square root you choose. And this is a complex number, and square roots of complex number you know how to take. So you can compute Z1 and Z2 now from this.
why not we just define them something like just x minus k and k z1 z2 zi zj and then apply lemma 3? Why doesn't that work?
What thing?
defining them something like x minus xj, just that x minus 2 times xj. Why doesn't that work?
No, but okay, so what happens? You get that there is some xij which is a complex number. Then you get there is like n times xij which is a complex number. Well,
Oh,
there is
okay,
no
yeah.
issue
It's
there.
not necessary that the first P0 also has a, yes, makes sense.
It's like
The
possible.
PHP I didn't want to.
Okay. Okay, so ignoring the part that I just declared that C star exists, which I will prove that C star exists, ignoring that part, is the rest of the proof clear so far? I will prove that C star exists, but assuming C star exists, if there's any questions, ask.
Can you explain the symmetric polynomials part again? How we get real coefficients for taking product of.
Okay, sure. Wait, let's work through an example. Okay. Yeah, 6 is fine. No, 6 is not fine, but I'll do it. So x minus z1 minus z2, x minus z1 minus z3, and so on. So what will its, say, constant term be? Constant term will be z1 plus z2 time, okay, minus, but I don't care about the sign. z1 plus z3, so on, up to z5 plus z6. Like the product of all 15 terms, right?
Yeah.
So since like it doesn't matter which order you label z1, z2, z3, z4, z5, z6 in, even if you permute them, you still end up with the same expression. So this polynomial is symmetric, correct?
You look at the individual coefficients of x to the power n, and since each of the coefficients is symmetric, and you can write it in terms of the original symmetric.
Yes.
With the symmetric function, you can show that they're real, right?
Yeah.
Right. Okay.
Do you understand?
Yeah, I got it.
It's clear now? Okay, good. Okay. Any other questions in this proof? Except C star. I will address C star.
Yeah, no, like the what? How did you do stuff with P0? That thing.
With P0. Wait, which
What
part?
like what did you do with P0, and like can you just
Okay.
explain this P0 till P1?
I'll just explain P0. Okay, the proof is okay, almost I'll write down the final details, but this is the main part of the proof. So P0, do you understand the definition of P0? It's this product.
Yeah.
Now, every coefficient of P0 is real. Do you understand that?
Yeah, how's that?
A bit like what we did here, right? When you expand P0, every coefficient will come out to be a symmetric polynomial in Z1, Z2, Z3, Z4, Z5, Z6. Right?
Okay.
So you can write this in terms of row 1, row 2, row 3, row 4, row 5, row 6. Right? But row 1, row 2, row 3, row 4, row 5, row 6 are real by Vieta. P of x was a real
Okay, yeah,
polynomial.
Okay.
Aryan, is this clear?
Yeah.
Yeah. Since this is a real polynomial and it has odd degree, we know it must have a complex root. In fact, we know it must have a real root, but I don't care. It must have a complex root.
Okay, makes sense.
And we know its roots are zi plus zj, all of them.
Yes.
So some zi plus zj is a complex number, which is the conclusion.
Okay, makes sense. Now you define P1 and then you do that.
Like you get the same thing. You get something of this form is a complex number again and again.
Okay, and then you apply lemma 3. Okay.
You apply lemma 3. Okay. Yeah. So now for the finish of the proof, so you have proven for 2 times odd. Now do the same thing. For any number that's 4 times odd, you define the same kind of polynomials. NC2 this time will be 2 times odd. Like the point is, if n equal 2k, then NC2 equal k times 2k minus 1. So like whatever power of 2 was in the k, that's the power of 2 here. But like n had 1 plus that power. So the power of 2 has decreased by 1. So you can induct. So now you will prove every polynomial that's like degree is 4 times odd has a root. Then everything that's 8 times odd has a root, and so on. Induction. Any questions? Kushagan, do you understand how the proof is completed?
Yeah, I do.
You do now? Yeah, good. Okay, if there are no further questions, I will now go to constructing C star. Okay. Do we want to go into constructing C star?
Yes.
Very well then. So before we go to C star, we'll go to our old friend C again. How did we get to C? So we had the real numbers. We noticed that x square plus 1 has no roots in reals. So we wanted to go from R to C,
We
right?
define iota.
Yes. So we define its root to be I. We say it has a root I. Now, we want we are trying to construct the complex numbers right now. So what do we want the complex numbers to be? We want real numbers to be a part of the complex numbers, right? We want I
We
to be a part of the
define
complex
iota.
numbers because we want it to something to satisfy this. And I is such that I square plus 1 is 0, right? For the only way this is works as a number system is if you are able to add sum of everything is there, product of everything is there, and you can divide by non-zero stuff and you can subtract, right? We want all of these operations to make sense. Correct.
Yeah.
Okay. So in fact, since we can add and since we can multiply, we will get all numbers of the form a plus. Yeah, okay. So a field is anything where you can add, where you can multiply, where you can subtract, and where you can divide by non-zero terms. That is a definition of a field. And the reason we want everything to be a field is the theorems about polynomials that I have implicitly been using, like factor theorem and other stuff. Their proofs require just addition, subtraction, division, multiplication. So if there's any set where you can do those, you can just use factor theorem without thinking about it. And all the other facts of polynomials that I'm sure I have used and not even thought about them. Okay, Kushagra?
Yes.
Yes. So since you can ignore I square plus 1 equals 0 for not, suppose we are just trying to add the number I to the complex numbers, right? So since we need to be able to add and multiply, we need I. Since we have I, we will have I square. Okay, we know I square is -1, but we know I square should exist in our set, right? We know I cube should exist. We know I4 to exist. Never mind the fact that we already know these are -1 and stuff. We know they should exist. And since we can multiply and stuff, we know all combinations of these exist. So we know if a1 to an are real numbers, then a1 plus a2i plus a3i square plus all the way to a and I to the n. We know that all numbers of this form should exist in C, right? We have not gone to division yet. Just due to addition, subtraction, and multiplication, we know all numbers of this form exist in C. Should exist.
Yeah.
Right. So in fact, we can say C contains, these are just all polynomials in I. We can say that C is the set of all polynomials in I. C is equivalent to Rx. But instead of X, we are using the letter I. Right. But this isn't enough. We didn't use one fact. We have never explicitly said that why I square plus 1 is 0. We never used that yet, right?
Yes, we haven't used it.
So thing is, so C, we know C should contain all polynomials of the form, all polynomials in I, but a lot of them we know are redundant. Containing I square plus 1 doesn't really matter because it already contains 0. They're the same thing. Right. So in
Are you
fact,
going to do some division thing or something?
yes, precisely. So the thing is, since we want I to satisfy I square plus 1 equals 0, what we need is any polynomial that's a multiple of I square plus 1. We say that's we define this equivalence relation. Take any two things in Ri, say P and Q. P and Q are elements of Ri. We say that P is the same as Q if I square plus 1 as a polynomial divides p minus q.
Okay, what?
Okay, wait. Okay, let's back up. Let's back up a little. Okay. So we have all possible polynomials in I. We know these should exist in complex numbers, but we know we are being redundant quite a bit. Right.
Okay. Yes.
We are being very redundant. So take any, like, the thing is, if you are given any random polynomial in I, you won't like leave it like that. You will take any term which has like a degree of I greater than 2. So if it's I square, you'll be like, oh, get rid of this. We know this has to be same as minus A3 because we want I square to be minus 1. That's how we defined I. Right. Similarly, when you see I cube, you're like, oh, like since I square is minus 1, this has to be same as like minus A for I. Right.
Yeah.
And any given expression, you will keep using like these reduction formulas till you get down to just like one term and the linear term.
Okay, yes.
Correct?
So basically, you
But
want to go down to all i's, right?
yeah, you want to go down to just like
Constant and linear, yes.
constant and linear. I mean, just a linear factor. So like you can just do this normally, but you can do this in like a more systematic way. So we know that this is a polynomial in I, right? So by like division lemma, like by polynomial division, you can write this like, okay, keep using I. You divide this by the polynomial I square plus 1. You get like some factor q of I. And you know the remainder will be like c plus d. Remainder has to have degree less than 2. Right? That's how polynomial division works.
Yes.
Right. So instead of like using the reduction formulas, I say whenever you are given a polynomial in Ri, you just take its remainder on division by I square plus 1. Like it's the same as using the reduction formulas. That's basically what you're doing, right?
Okay.
What?
Yeah, okay.
Yeah.
So everyone understands like why taking the remainder is the same as this is the quotient ring. Yeah, but I can't say quotient ring, okay? I'm trying to build it up. I know you know higher math, but a lot of people in this class have not studied quotient rings. You are correct. Factor theorem. Oh, wait, no, not factor theorem. Anyway. So we can say that like we have the set Ri, but if instead of we don't take every element in Ri, we say every element is the same. Like if two elements give the same remainder on division by I square plus 1, they are the same element. Does this remind you of anything?
So like the quotients don't matter, like QI doesn't matter.
Yeah, because the point is we want I square plus 1 to be 0, right? So no matter what Qi is, this whole term we are saying this is just 0. I don't care.
Okay, I square plus 1 is 0. Okay, damn.
Yes, exactly. That's
But
how we are
how are
trying
you
to define.
dividing by 0? How are you dividing by 0?
Yeah, okay, so like not. So like what I should actually be saying, so like take the way I'm going to define like the complex numbers is start with Rx, just the ring of polynomials, just a set of all polynomials. We say two polynomials are the same if they give the same remainder on division by x square plus 1, right?
Okay.
If they are equal mod x square plus 1.
Okay.
Right. And if they are the same, so the complex numbers are Rx with this additional restriction that division by x square plus 1 makes numbers like we only care about remainders mod x square plus 1. It is similar to how you define like numbers modulo a prime. Like to define numbers modulo 5, you start with all numbers, and you say if two numbers differ by a multiple of 5, then we just say they are the equal numbers.
Okay, so you just like if they differ by multiple of x square plus 1, they're equal.
They're equal. We define that.
Okay.
And so that's how we get C. So like in notation, what we say is you start with Rx, and wait, do you use curly brackets here or square brackets? I think you use like parentheses. Yeah. So in notation, you say that C is like the same as take the ring of polynomials and declare that if two things differ by multiple of x square plus 1, they are the same. Like this is exactly the same as defining numbers mod sum prime. So like if two numbers differ by a multiple of 5, they are the same. You denote that by z by 5z, right? So this is the set, and 5z is all the numbers you are saying are now 0. So Rx is the set, and x square plus 1 is what you are declaring to be 0.
Okay. Okay.
Okay?
Yeah.
Okay, is that clear? So this, we have, okay, I have not yet proven that complex numbers have division. I'll get to that. But just with this knowledge, you can sort of guess the definition for like C star in general.
Yeah, so
Take,
that's 3x and something to be 0.
can you sum this thing up? If time allows, can you sum this thing up? I can try. This, yes, I hope not too many people are lost. This is, the remainder is same. How exact, if remainder is same, how is the polynomial going to be exactly same? It's not. But the thing is, we don't care, right? Because, wait, what? Wait, Rudansh, I don't get it. Polynomials can be different. But the thing is, they evaluate to the same value. Because I square plus 1, we want to be 0. If two polynomials differ by I square plus 1, we still say they refer to the same complex number.
I think if you say I square plus 1, that 0 term is confusing a lot. So you can just say x square plus 1.
X square plus 1, x square plus 1. It's modular polynomial. Yeah. The thing is, so I'm associating every complex number with all the polynomials that mapped, like, if you plug in I, you get that complex number.
Yeah.
Right. That's how I'm doing it.
Wait, so for C star, do you take all the polynomials modulo your original polynomials with which you're trying to find complexes?
Correct. That is perfect. So you have C, you consider all polynomials in C of x, and then you declare that whatever our original polynomial was is now 0. So you say
Okay,
that
but
any
this
polynomial.
Yeah, this original polynomial can be many, right? What is the one polynomial we're working with? Like
Whichever you're trying to, like, so what we did here was like, we had some 6-degree polynomial. We want to prove it has a root. So we went to C star. Like, depending on which polynomial you start with, you will get a different C star.
Okay, yes, makes sense.
Right. So the way we do it is, once again, we take all possible polynomials and then we declare that two of them are same if they differ by a multiple of p. Okay. So that will be like, so suppose you have, what's the random one? X to the 5. Like this might, like this obviously has roots, but suppose it didn't have roots. Then we introduce its root, call it k. Right. We introduce its root, we call it k. Now we know that since we want to be able to add, multiply, divide, subtract, we want to have all numbers of the form like ai times k to the I, right? But whenever you get k to the 6, you will replace it by minus 3 k cube minus 1. Because
Reducing the
we know
degree
we want k to be a root of this.
So the same equivalent argument.
Yes, exactly the same argument. So instead of like doing this replacement argument, you say I divide my polynomial by p and I take whatever remainder I get.
Okay, yes, that makes sense.
Okay, is everything clear? Okay,
Kind
not
of.
everything.
Yeah.
I hope, okay, some people seem to be following, but if anyone else has any questions,
Division.
ask. Division, yeah. I have not proven division yet. Okay. So before we go to division, I have to like make one additional restriction. So the thing is, okay, suppose we had, I mean, okay,
I have one question.
Yeah.
P of x, if we want to represent a number, let's say, uh, 6 times k to the power 4, then what exactly is it? I mean, I can't.
It is 6 times k to the 4, where k is defined as a root of this polynomial. It's exactly as you do complex numbers. What is 5i? It is 5 times I, where I is defined as a number whose square is minus 1.
But then why do you have to reduce all the polynomials modulo our original polynomial? Like,
Okay, the thing is like, Yeah, you can refer to 5i as 5i to the 5 or 5i plus I square plus 1. Yeah, I can, yeah. So the thing is you can write it in all these ways, but you want to write it in like the easiest possible way for convenience.
For convenience, not for.
I mean,
Hmm.
what I'm actually like, I'm not reducing. What I'm actually saying is if two polynomials differ by a multiple of p, they are this. I'm just calling them equal. Equal as elements of C star. They are just equal, right?
Okay.
I say two things are equal if they differ by an element of like, if they differ by a multiple of this.
So
And
where are
like,
we using this? That's what I'm asking.
what?
Where are we using the fact that two polynomials are equivalent when they differ by a multiple of?
I'll get to that's useful when you prove division.
Okay.
Huh. Okay, so first of all, one thing I'll like fix here is if like like x minus 1, this already has a root. So like you can't go on and say like, oh, I'll take cx mod x minus 1. Like x minus 1 obviously already has a root, right? And suppose we started with like some okay, like take x square plus 5x plus like 1 times x square plus 2x plus 9 or whatever. Okay. Okay, this does have roots, but like ignore. The point is if you have a product of two polynomials, then instead of like, say, suppose this was our p. Suppose our p factored into like a product of three quadratic terms, right? Then instead of like just constructing everything with p, you can just construct p with one of like C star with one of its factors. Right. So like you want p to have a root. That's equivalent as saying having one of its factors has a root. So like pick any of its factors and define C star to be like Cx mod like x squared plus 2x plus 9. Like the idea is you can, without loss of generality, assume p was irreducible.
Okay, can I just repeat this part?
So like, okay, I said earlier that C star is where p factors completely, right?
Yeah.
I like, okay, so before we get to C stars, I'm actually like trying to construct like a weaker version. Just like a set where P star has a root. Like I'll get to all six roots eventually. Sorry, where P has a root. I'll get to all six roots eventually. Currently, I just want it to have one root. Okay.
Okay, like P has one root in C star, you're just saying that.
I just want to construct a set C square such that P has one root.
Okay.
Right. So now the thing is, if P was like factorable, instead of constructing this, like doing this whole process with P, I'll do it with one of the factors of P. And I will ensure one of the factors of P has a root, because then P has a root.
Yeah, works.
Just answer a question in chat about like weird notation. Like for some reason, like the notation of when you do this with Z, it's written as Z by 5Z, but you don't write like times Rx here. It's just notation. Someone decided it was this way. Don't ask me why. Anyway, so the point is, so like without loss of generality, assume P was irreducible. Okay.
Wait, irreducible in complex numbers, right?
Irreducible in C. And like we have specifically, like in C star, it will be reducible because of how we have made it. Okay. Now we need division. Okay, so division is just like multiplication by the inverse, right? So if we can just prove inverses exist, we are done. Like given any polynomial p, if we find a polynomial q such that pq is 1, we are done. Because then whenever we want to find like...
In C star?
What?
In C star? Like PQ is 1 in C star?
Yeah, it's in C star. Everything is happening in C star. Like
Okay.
now everything. So like P is an element of C star. If we can find the Q in C star such that PQ is 1, then whenever we want to find X by P, we will just find X times Q. And we know how to multiply. Right? Multiplication we are very happy doing. Just
One
multiply them like polynomials.
is one in C star.
What?
Is the number one in C star?
Yeah. Like it's not just one anymore. Like the constant polynomials are polynomials, right? Cx contains the polynomial 1, and if you reduce it modulo p, it is still the polynomial 1. And
Okay.
like 1 is the same as 1 plus p, and the same as 1 plus 7p. Like I'll denote it by 1, but it is the same as all these numbers. All these numbers in C star are the same. Okay?
Yes.
I hope I'm making sense. Anyway, so we want to just prove that there is some q such that pq is 1. Right? Like pq is 1 in C star. That's what we want to prove. PQ is the same as 1 in C star. Which is another way of... Okay, wait, no, sorry. I shouldn't be using P here. That might be a confusion because P I'm using as like... Okay. So we take C star to be Cx, but we declare P to be 0. Right? Given any... I'll just say A. Given any A in C star, we want to find B in C star such that AB equal 1 in C star. Okay? This is what we want to do. Is it clear? Is that clear?
Yeah.
Good. Now, AB equal 1 in C star means like just three. Let's think of A and B as polynomials. That means AB and 1, like in CX, they are not necessarily equal, but we know they differ by a multiple of P. Right?
Yeah.
By say H times P.
H, yeah.
Yeah. So like in other words, we want to find like B and H such that AB minus HP is 1. That's what we want to do. We want to find polynomials B and H
In
such
C,
that AB
in
minus
C.
HP. What?
This is in C. This is in C.
Yeah, this is in C, in just C of X. Like,
Yeah.
if we can find... So like, okay, A is an element of C star. Take the corresponding polynomial in C of X. Right. Now in C of X, find polynomials B and H such that AB minus HP... Oh yeah, my handwriting is like bad. It's fine. AB minus HP is 1. Find polynomials like that.
Shouldn't we
And of course,
find... Wait, shouldn't we find P because we have defined C star to be Cx by H?
no, P. Oh, my
Okay.
handwriting sucks. This is P, guys. That was P. I'm sorry. My handwriting. Oh, agreed. Okay. You don't have to like hurt me like that. But yeah, we find B and H in just C of X such that AB minus HP is 1. And once we have found them, now we think of like B as an element of C star, and then HP in C star is just 0. So AB in C star is just 1. Is that clear?
So B does not necessarily have to be in C, right?
Yeah, it has to be in C of X. It has to be a polynomial in C.
Yeah. But if it even was a polynomial in C star of X, we would still be fine, right? I mean, that's what.
It was a polynomial in? Yeah. I mean, it doesn't have to be a pure complex number. That's fine.
Okay.
It doesn't have to be a pure complex. It can be like the inverse of 1 plus 2i won't be a real number. It will be 1 minus 2i by 5. Right, we are fine with that. Like this is a polynomial in I. Its inverse will be a polynomial in I.
Yeah. What I ask is that here you said you have to find B in C of X.
Yeah.
That's like a stronger condition, right? Pardon.
No, it's weaker because like in C of X, like I'm sorry, wait, what?
I'm saying that for B being in C of X, we basically want to show that A has an inverse, right? That's all we want to show.
Yeah.
Why are we trying to show that B is in Cx, not in C star of X?
No, see, like whatever B is in C of X, it is like it corresponds to some element of C star after you reduce it modulo P.
Okay, like that. After reduction. Yeah.
I
Okay.
mean, you don't even have to do reduction. Like technically, you can like write the inverse of 1 plus 2i as 1 minus 2i by 5 plus I square plus 1. If you
Yeah.
say this is the inverse, people will think you are weird, but this is a valid inverse.
Okay. Yeah, I got it.
Got it? Just whenever in doubt, go back to C and think about what's happening. Once a wise man said that to an English. No. You have to ask questions. If you have any questions so far, ask. But okay. So let's go back to what we are doing. So
Okay,
now we
how
have
is that?
polynomial.
How is that the inverse?
What?
Like, okay, wait, you just rationalized?
What's rationalized?
You just rationalize 1 plus 2i? Like, how is one?
Like the thing is 1 by 1 plus 2i, like we want all complex numbers to be in that form, right? We don't want them to be in a form where there's a denominator. Like
Okay.
nowhere have I like allowed like 1 by x to exist in C star. It does exist, but like the point I'm trying to prove rationalization is a thing, basically.
Okay, so
But
like
like
you will want to rationalize AB minus HP.
no. I'll try to rationalize 1 minus a, but the way I'm doing it is very weird.
Okay.
Like the way I'll do it is like multiply both numerator and denominator by b, and then b denominator will become 1 plus hp, but like p is 0, so this is just b. I want to prove like such a b exists such that this becomes 1 plus hp. Okay? That's better. Anyway, let's go back. Weird, but makes sense. Yes, okay. That's a relief. So now our statement reduces to proving A is a polynomial in Cx, P is another polynomial in Cx. We have to show to prove there exists P and H in Cx such that B times A minus H times P is 1. This is what we want to prove.
Yeah.
Okay. One thing. We know 0 doesn't have an inverse. How do we encode the condition that A is not the 0? Like A unequal 0 in C star. What does this mean? Like, how do we encode that?
Yeah, so it's A is not a multiple of P.
Yes, P does not divide A. Further, P is irreducible. We assumed that.
Yeah,
right?
because otherwise the factors of P also might divide is.
Yeah, exactly. So P is irreducible. So like, in fact, that means P and A are co-prime.
Yeah. P is irreducible in C.
Bro, you can't just say a polynomial and another polynomial is co-prime just and live with it. Like, how do you defining the GCD? Bro?
Okay, you don't find Bezos spell.
P is irreducible in C. Right.
C of
Because it
C
is
of X.
reducible.
C
Yeah,
of
If
X.
because
P
it is
wasn't
reducible.
irreducible, won't P be done? Like we'll have a smaller degree thing, right? Because
Yes, exactly. That's why as you started assuming P is irreducible. Right.
Okay, yes, makes sense.
Mhm.
and how do you have GTD of P comma A equal to 1? And how do you define
Okay,
this
so
set, like as Aryan asked?
GCD. Okay. Let's do we dwell on that? How do I explain? Okay, so GCD of polynomials is just like exactly that. Like the GCD, like how is normal GCD defined? CST tensed by how is okay. So let's go back to Z to remind us of what GCD is. We say GCD of AB is G if G divides A, G divides B, and G is the largest number that does that. Right?
Okay.
Yeah, but wait, can't we do Bezos and then show that it
Okay,
like
no,
can't we
like
define using Bezos?
the problem with is this: how do you define a largest polynomial?
Correct.
Compare.
So what we do now for polynomials, we define largest by degree. So like, but the thing is like polynomials of same degree exist. So GCD of PA is 1 or 2 or 3. So like GCD in polynomials is only defined up to multiplication by constant. You take the polynomial of the largest degree. We can't be going over for it. It's fine.
So why do if you take two polynomials to be of the highest degree and they divide both of the polynomials, why do they both have to be
multiples of each other?
Yeah.
Is there a non-trivial way to say this? That's wait, how would I? What's the easiest way to say that? Left as an exercise. No, I can show it. It's hmm, yeah, no, yeah, multiple of roots. Yeah, so guys should accept for now because things don't always make you well. I mean, he has a point. Okay, I'll come back to this. You have a point, but we don't have to like worry here because P is irreducible. Right, so like, and the only polynomial that can divide P is 1 or P and their multiples. That's what it means to be irreducible. Oh yeah, because unique factorization, by the way, yeah. Okay, I'll get to it. I will get to it anyway. Yeah. So I'm trying to think if there's like a better way to do this. There's another definition of GCD like slightly better here. Can
Can we define it using bezels? I'm just curious.
Yeah, I think that will be a better idea. Okay. Instead of bezels, I'll do like a 2s giving a subset of paper. In fact, like, do I even need to like do all this? Can't I just prove the roots? Even in fact, I don't even think I need to define the GCD. Yeah, okay. Like, so the intuition is GCD, but if you're like worried about the definition, we'll like ignore it for now. If you remember,
It could be definable. Like, I guess we had a higher math class in which this was proved
oh,
or something.
it was. Yeah, but okay, here's the thing. I can't, for some reason, I'm skill issuing right now and I won't bother. I'll just directly do shit. Okay. So if you look here carefully, Gauss can't be wrong. True, true. If you look here carefully, A and B, they are like this. This looks a lot like Bezout's lemma, right? You start with two numbers, you take some linear combination of them, and you get one, right?
Yeah.
This looks a lot like Bezout's lemma.
Yeah, it does. It does look like a lot like Bezout's lemma.
Okay. What proof of Bezout's lemma do you guys know? There are two, and both of them work here.
Assume something was. Wait, okay, I forgot the proof.
GCD algorithm backtrack.
Yes, GCD algorithm backtrack. Correct. That will work here. So take A, take P, right? And we like okay. So yeah. So whatever has the largest degree, you write it as A equal P times Q plus R. R will have a smaller degree than A. Then you write Q. No. Sorry. Yeah. R will have a smaller degree than P. Right. So now you write P as R times Q2 plus R dash, and R dash will have a smaller degree than P. R dash will have a smaller degree than R. Yeah. Then you write R equal R dash times Q3 plus R double dash. And R double dash will have a smaller degree than R dash. Right?
Yeah, just write R1, R2.
Yes, and
you
you
have
keep
a,
going like this.
you have a point. You have a point. R1, R2. So like you're basically doing that's what you like start do in Oh no. This is bad. This is like this requires you. I'll use the other proof, please. Okay.
This requires GCD.
Like because the thing is, the point is Euclid's the algorithm ends on GCD, right?
Yeah, but no, you could keep track of the tuple. Like you express it in terms of A and B, no?
Okay, I don't know why I canceled it out. I'm
And
still
keep track of the tuple. Like
we just
That's
accept the
what do.
proof.
Just
Yeah,
undo.
but okay, this is the last thing I have to do, so I might as well do it. Yeah, okay. Thank you for helping. So we have AQ. Like we start with the tuple AQ, then we get the AP, then we get the tuple P comma R, right? Then we get the tuple uh, R comma what's the next one? Whatever, R2. Then we'll get R2 comma R3. And like the degree of R keeps decreasing. So eventually it will be 0. Right?
Yes.
So it will become like Rn comma 0. That means Rn will be like take the step before that. Rn minus 1 Rn. So yeah, so
R is a multiple factor.
yeah,
Okay.
so it will be like Rn times Qn plus 0. So
Yes.
Rn divides Rn minus 1. Right. And before that, you had Rn minus 2 equal Rn minus 1 times Qn plus Rn, right?
Yes.
And Rn divides this and this, so Rn divides this. So by induction, you can prove that Rn must have divided everything.
Wow, okay.
Yeah.
Right. So Rn divides P, but P is irreducible. So Rn is either P or a constant. If Rn was P, then P divides A and A is 0. We know that's not true. So
Yeah.
Rn must be constant. And like you can scale it so it's 1.
Yes.
Yes. And now you substitute back. So like you substitute the value of R yeah. So Rn is 1. Right. So you write Rn equal Rn minus 2 minus Rn minus 1.
Wait. How did you scale so that the constant turned into 1?
Okay, ignore that. So we just have Rn, which is a constant. Okay.
Okay.
So at the end of this proof, instead of BQ, like this being 1, we will have it equal constant. Then we divide both sides by C. And instead of picking B, we pick B by C and H by C.
Okay, and that turns 1. Okay, fine. Nice.
Yeah. So now Rn is Rn minus 2 minus Rn minus 1 times Qn. So we can write Rn in terms of Rn minus 2 and Rn minus 1. Then you, like from the previous expression, you substitute the value of Rn minus 1. Then you substitute the value of Rn minus 2. And you keep doing that till all you're left with is like something in A plus something in P. And we are done. I skill issued at the end there, but that works. Is that clear? Does everyone understand?
yes.
Yes.
Wait. Okay. Who followed that proof from the beginning to the end? Everything is clear. Amazing.
Just GCD.
Geez, ignore, like we don't need it. Like the point is we have proven fundamental theorem of algebra. Ignore the fact that GCD was like stupid there. I forgot how it worked.
So this proof was sort of very, I would like to say hard.
Oh, this is a hard proof, but the point is I don't need to create any crazy theorems. This is like the only crazy theorem I needed to create. And like this is sort of intuitive, right? Like complex numbers exist. Surely you can create something forever.
Yeah, that was intuitive, but I
Okay.
don't know how you motivate those polynomials like P0, P1.
Oh, that part, yeah. The point of this proof is all the hard parts are elementary. This entire idea is completely elementary, and it's like very Olympiad like. It's also
Yeah.
completely impossible to come up with, but
Sure.
that's a
Yes.
minor issue.
Yes, exactly. It's impossible to come up with.
Impossible. It's a minor issue. So this proof
The
was
last time I was like, this was when Anant showed us the proof for the irrationality of pi, and I still have no idea how did a human come up with that.
I have not seen actually. Which proof was that?
I don't know. There was some weird name which I forgot. Wait, let me see if I have the name.
Yeah.
Wait.
I'll rewatch C star part in recording because in the middle I lost track. GCD made me alive again. Okay, wait. The import like ignore C star part. Before C star part, does everyone understand? Assume the existence of C star.
Yeah, it's the proofs. The proof is by a guy named Miklos Laxov Markovich.
Okay.
Like before
I'll
C star, everything was clear. In C star, like you introduced all the concept from ring fields to like you just tried to introduce everything.
yeah, I know. That
Wait,
was
wait,
I could have done that better in hindsight,
But
but
you said
Gauss
for proving
definitely did
GCD,
follow up your proof.
what? Kushagra?
Gauss definitely did follow up with your.
GCD, yeah, see, of course,
Okay, whose
Gauss.
like
proof is this? Whose proof is this? Whose proof
I
is this?
don't know who has come up with this proof. I was told this proof by Rohan Goyal in IMOTC 2024. Rohan Goyal stopped here. Like, Rohan Goyal never proved C star. I had to fill in those gaps, but Rohan Goyal stopped.
Wait, you did this all by yourself, this C star shit?
Stista shit. Yeah, I mean, no. I did this because I already had a lot of knowledge of ring theory. Like this notation that we are using here, like that's like general quotient ring notation. I already knew that. The only thing I had to prove was that like division is allowed, and I already knew polynomials follow Bezoots.
wait. Now my question. You
Yeah,
for
Lavish.
GCD using do it using fundamental theorem algebra, right?
Yes.
But for that, like with GCD we proved the C star, and with C star we proved fundamental theorem of algebra. Isn't that a cycle,
Yes.
right?
Oh, by the way, one thing I should forgot to mention. Okay. We have only shown like so we had a polynomial p that was like degree 6. We wanted to have 6 roots. In C it has none. We go to C star where it has one, at least one, right? But we
Yeah.
wanted to have 6. So what you do is you go to C star star. You keep doing this till it has all the roots you need.
Oh, God.
It's fine. Like the exact same algorithm
Yeah.
works. There is
Now just see that P is 5 degrees.
Yeah,
yeah,
That's
people
finite. You
realize
only need finitely many steps. It's fine.
people realizing induction is powerful.
When do we end class? I don't know. I'm free. I can like how many questions you have, you can ask. Any question
no,
about that.
but how does
Yeah,
that
basically, I
work?
wanted to ask
Like,
you a question about unimax.
One by one, one by one. Lavish, I'll start with you.
yeah, the GCD proving, you said GCD can be proved using fundamental theorem of
No,
algebra.
yeah, that's I was about to say that, then I realized, okay, no, we should not do that. But like, no, the final proof I wrote, I did not cite GCD at all. I just did division, right?
Ah, okay,
So
yes.
like this proof works. So if you theoretically want, you first do this proof, then you prove the fundamental theorem of algebra, then you come
Then
back and prove
GCD.
GCD. But
Okay.
GCD has easier ways to prove. I just can't remember them for
Yeah,
now.
there were some ways. Even
Wait,
I
what's
know.
the other proof? Wait, why are the two? I've only heard of this
Oh,
tuple
oh.
one.
Like if you might know, like there's one proof of Bezout's lemma is considered a set of all possible values of ax plus by
Correct. Yeah, the how
and pick the
many?
smallest.
Yeah, you choose the smallest one.
Yeah, so like you do the same with polynomials. You choose the one with smallest degree.
Well-ordering principle.
Yeah. And then you
Wait,
prove
what?
that it,
But how does that satisfy?
yeah, but the thing is like ax plus by equals say d has the smallest degree. Right? And like let's go back to original notation. B time, okay, I'll use x as some polynomial, y as some polynomial, and a and p are the things we had, equal d, and d is the minimum possible degree, right?
Sure.
So like write x equal dq plus r, right? So r is equal to x minus dq, and you can write d as xa plus yp. So like this entire number you can write as like x prime a plus y prime p, right? So sorry, not X. A. My bad. Yeah. It's like R you can also write in terms of A and P, right?
Sure.
But then R has a smaller degree than D, so R must be 0. We want, because we assume D has the smallest degree.
Wait, what? Wait, there were too many variables in too short time. What?
D is the smallest possible non-zero polynomial in terms
Correct.
of
Yes.
degree. We write polynomial A as dq plus R.
Correct. R has less degree than D. Okay.
R has less degree than D. And then we write D as xa plus yp, substitute it here.
Okay.
Take everything to that side and you will get R as A times something plus P times something.
Oh, R is less. Okay. Yeah. Okay.
Yeah.
Makes
So like
sense.
R must be 0, hence D divides A, and then D divides P. And since it divides
Okay.
both, it is a constant.
Ah, I see.
This is the second proof. I like this. I like this better. But someone mentioned the other one first, and I was like, I'll go with that. And then I forgot. It's fine. Yeah, that's second question. Third question. So anyone else with questions? Any with anything in the class before I anything.
We didn't really use lemma 3, right? Like,
Lemma 3 we did, right? That's what.
but like we didn't define it like properly, and then we used it, and then we like defined it.
Yeah,
like,
but you actually didn't. You need to use lemma 3 because you could just use the quadratic formula.
Yeah,
I don't know.
proof of lemma 3 is quadratic formula. What do
quadratic
you
formula.
think?
Okay.
It's not a large lemma. The only lemma that was larger was I declared it a theorem instead. Okay, was there what was lemma 1? Okay, lemma 1 was like slightly large, but like it's also lemma.
Okay, for lemma 2, like you said that the z1 plus z2 belong to the set of complex numbers as well as z1, z2. So
That's lemma.
can't like z1 and z2 be 3 and z1 be 3 and z2 be like say 4 iota and still the conditions would be satisfied?
Yeah.
Yeah, but
A plus
3
B is
is
complex,
complex.
A B is complex, and A and B are complex. I don't care
Okay, yeah,
about.
so you still consider 3 to be complex number?
Yeah. R is a subset of C.
Oh, okay, yeah.
R in C. 3 is complex.
Okay. Okay, like are you studying topology in uni or you can't take it in the first year?
I can't, I mean, I do not care about what I can take in the first year. I go to whatever lecture I can, but topology doesn't happen in this term. I think topology is like very weird here. I think I
Like,
can
can
only.
you go in any lecture you want?
Oh yeah. I'm freely going. Does there exist some number that is not complex? Excellent question. What do you mean a number? What do you mean by number? Yeah, I can I'm I'll come back to the branch. I can go into any lecture that in uni. Like Imperial is very free. Like I don't even have to go to any lectures at all. Just have to show up for the exams. No. So no, there are numbers that are not complex, but it depends on what you mean by number. Like, yeah, what do you mean by a number?
Okay, like, can you recommend me? Like, I just wanted to study a little bit higher maths apart from Oli maths. So, can like you
Napkin.
recommend from what to start?
Napkin. Oh, can I stop the
Yeah, yeah. I
recording?
mean, I know Napkin is a very good place. Like, what? Like algebraic, like abstract algebra or differential geometry, or I'm bad.
Wait, how do I stop that? Differential? No, just abstract all napkin. Like napkin covers.
Study napkin. It's very, very good.
Honestly, napkin. Like napkin has like recommended reading at some points. You can look at them.
Yeah.
Bro, you can stop the recording now.
Yeah. Stop. How do I stop? Where is the stop recording button?
You did start recording, if I recall correctly.
Yes. Atharva Sutar did. And can I stop it? Wait. Ah,